In this lecture, we start a new module on the types of device models. Now, does every problem have a unique solution? Well, the answer is yes and no. It depends on the situation or the problem. For example, in the school days in physics, we have solved the problem of collision between two balls. So, this two body collision problem, it has a unique solution and a unique approach of getting the solution. On the other hand, consider the situation in a semiconductor device. You have millions of electrons and holes moving about randomly, colliding with each other and with other particles like randomly located dopants, phonons, and so on. And then you are applying various forces to the device. For example, you may be applying an AC voltage, a high frequency voltage, or a low frequency voltage, a DC voltage, and so on. So, you have a variety of situations, and the conditions in the device are complex. In this kind of a problem, you do not have a unique solution. Although the underlying physical laws are unique. For example, if you want to solve a two body problem in the school physics curriculum, you use Newton's laws. If you want to solve the problem of deriving the current in response to a voltage in a semiconductor device where millions of particles are colliding with each other, moving randomly, you can start from either Newton's laws or Schrödinger's equation. However, starting from the fundamental laws and getting an equation for current as a function of voltage, this journey is rather difficult and long, and therefore many different approaches to getting models for device current as a function of voltage exist. There are different varieties of approximations to negotiate this difficulty of deriving the model from fundamental laws, and that is why you have various types of device models. Now, these are the types of models that we are going to look at. What are the types of models? So, at the end of this module, you should be able to describe the classification of device models based on the time rate of change or frequency of voltage or current variation, based on amplitude of voltage or current variation, based on the starting point of the derivation or attributes of the solution technique, models based on attributes of the mathematical function in the solution and attributes of the parameters and constants in the solution, and finally device models based on the application. You should be able to interpret from the jargon employed the type of model being addressed in any literature on device modeling, and finally you must be able to use the appropriate jargon to convey a particular type of device model. Jargon. Now, let us look at a number of words that are used in the context of device modeling. The words that we list here, most of them refer to some type of device model or the other. A few of them may refer to the type of function that is used in the model solution. We are going to list these words in alphabetical order. So, you have AC models, analog model, behavioral model, and black box model. So, against each of these words you must add the word model. Closed form, compact, DC, and digital are some more varieties of model. Then empirical, explicit, and high frequency models. So, here the word explicit refers to the form of the model equation. Implicit, this word also refers to the form of the model equation. Infinite series, form of the model equation. And then you have inverse modeling, large signal model, low frequency model, macro model, non quasi-static model, and numerical model, parametric, phenomenological, physical, predictive, process aware models. quasi-static model and rigorous model, scalable, small signal model, static model, sub-circuit model, and finally table lookup models, transcendental form of equation of a model, and transient models. So you see we have listed a number of words, a number of types of models. This list is not exhaustive, but nevertheless if you know these different words and their meanings, then you will feel comfortable reading the literature on device modeling. Now, since there are a variety of models and a large number of words are used in the context of modeling, to understand all these different types of models, it makes sense to classify and organize them. In scientific approach, whenever we are dealing with a complex reality and a variety of things, the first step in understanding them is to organize the things in groups. Okay? Now that is what we are doing here. So we begin with classification of models based on the time rate of change of voltage or current. Static or DC models are based on conditions which are constant with time in the device. On the other hand, quasi-static models are based on conditions which vary slowly with time. Now what are these conditions and how slowly should they be varying in order for the model to be called quasi-static? Let us answer these questions in the context of the drift diffusion model, because it is the drift diffusion model that we have said is the basis of all our device models in this course. The equations of this model are listed here. First, the static or DC model is based on the conditions of electrons, holes, and electric field which are constant with time. So dou n by dou t, that is this term here, dou p by dou t, that is this term, and dou e by dou t, the term here, all these terms are 0. So these are set to 0 here. This is a static or a DC model. In other words, if you start with these equations and then derive an equation for current as a function of voltage, then the model will be referred to as a static or a DC model. In contrast, let us look at the quasi-static model. Now here dou n by dou t, dou p by dou t, and dou e by dou t are not 0, but they are small. Now how small are they? So dou n by dou t is compared with delta n by tau. So this dou n by dou t is compared with this term, and now if this is very small compared to this term, then we say that the conditions are quasi-static. Now you might ask, why don't you compare with this term or this term? Well, you could compare with these terms. The advantage of comparing with this term is that you can see it has the form where the numerator is a concentration same as this term and the denominator is a time constant. So this comparison is rather easy. Now if this term is very small compared to this term, that suffices for us to neglect this term, right? We need not compare it with the other terms to decide whether the term can be neglected. Okay, now here we have used dou by dou t of delta n rather than n. The reason here is that on both sides we want to have the same concentration term. Now you know that dou n by dou t is equal to dou by dou t of delta n, because n is equal to n naught, the equilibrium value of electron concentration, plus delta n, that is the excess carrier concentration. So if you differentiate n with respect to t, since the equilibrium concentration n naught does not vary with time, dou n naught by dou t goes to 0, and therefore dou n by dou t is equal to dou delta n by dou t. Similar comments apply to this inequality in delta p. The Qi here refers to the inversion charge in a MOSFET, and tau tr is the transit time. This tau here and here is the same as the tau used here, which are minority carrier lifetimes. Now coming back to this dou by dou t of Qi much less than Qi by transit time. So this is the condition that is applicable in the context of MOSFETs. So a quasi-static MOSFET model is one in which the rate of change of inversion charge with time is much less than the inversion charge by transit time of carriers from source to drain. Now this topic was discussed in the module on characteristic lengths and time, that is module number 5. So please refer to that module and the discussion. Similarly, dou E by dou T is much less than E by dielectric relaxation time for quasi-static conditions. How do you get this relation? So here you are comparing this term which is being neglected with Jn plus Jp. Now Jn and Jp are given by diffusion plus drift components, right? So when you sum these up and put them here, you will get a diffusion component and a drift component, and the drift component would be sigma times E, where sigma is the conductivity due to both electrons as well as holes. So now you can compare sigma times E with this term, and if this term is very small compared to sigma times E, then you can neglect it, and this inequality leads you to the inequality dou E by dou T is much less than E by dielectric relaxation time. Even this fact has been discussed in module number 5 on characteristic lengths and time, where we have discussed about the dielectric relaxation time. Thus the quasi-static model assumes that the excess carrier concentrations delta n and delta p vary slowly on the scale of minority carrier lifetime tau. The inversion charge in the MOSFET varies slowly on the scale of transit time, and the electric field E varies slowly on the scale of dielectric relaxation time. For clarity, let me just mention that the inequality dou by dou T of Qi is much less than Qi by transit time can be obtained from the equation for electrons, that is the continuity equation for electrons or holes, depending on the inversion layer is because of electrons or holes. So assuming that inversion layer is because of electrons, you can derive this equation from this electron continuity equation by integrating this equation with respect to distance from source to drain. So when you integrate, the left hand side dou n by dou T becomes dou Qi by dou T, and when you integrate this term divergence of Jn over distance, you get a term representing the drain current, because you are integrating from source to drain, and that drain current term can be written as Qi by transit time. More details of this please refer to module number 5 on characteristic lengths and time. Now majority of the models are quasi-static because quasi-static approximations yield a reasonably accurate model for rapidly time varying device phenomena. So even when the conditions vary rapidly with time, you can use the solution of these conditions for quasi-static approximation and get a reasonably accurate model. Now how do you do that? Now this is how you can get it. The current as a function of time due to a time varying voltage V is modeled starting from the approximation distribution of holes, electrons and electric field over distance at any instant of time are approximately equal to the steady state conditions corresponding to the voltage at that instant of time. Let us assume a ramp voltage. So voltage is varying linearly with time, it is increasing. At an instant of time t, the voltage is V of t. Then what we are saying is, we will start with the assumption that P, N and E as a function of x at this instant of time can be obtained by assuming this voltage or this value of the voltage and assuming DC conditions corresponding to this voltage, and then solving for Px, Nx and Ex as a function of time. Now you can start from here, and ultimately the model will turn out to be of the form: the quasi-static current as a function of time is given by I as a function of the time varying voltage plus d by dt of a charge which is also a function of the time varying voltage, where I as a function of V is the current and Q as a function of V is the electron or hole charge stored in the device due to steady state bias voltage capital V. So how do you start from these conditions and get an equation which is of this form? Let us illustrate this with the help of a diode model. So let us say this is our diode and we are applying a ramp V as a function of t, and this is the current as a function of time. I want to get an expression for I as a function of time as a function of V as a function of time. So let us look at the conditions inside the p-n junction at any instant of time. We are looking at the distribution of excess carriers on the n side, because n side is lightly doped. P side is very heavily doped, so we neglect the excess carrier concentration on this side, it is going to be small. Now if I assume quasi-static conditions at any instant of time, if I have a certain voltage given by this value, for that voltage I am plotting these distributions. So this distribution plotted here is quasi-static, meaning it is obtained assuming that in this continuity equation dou by dou t of P is 0, and this dotted line excess carrier distribution as a function of x corresponds to non quasi-static conditions, which means this distribution is obtained by solving this continuity equation taking into account this dou P by dou t. The Jp on the right hand side is given by this diffusion current equation. We are using the diffusion approximation. Okay? From the first level course you know that minority carriers can be assumed to flow due to diffusion. So when you are solving this equation in the solution, the Jp term will be assumed to be due to diffusion. Let us explain these two distributions. From the first level course you know that this distribution, which is quasi-static or static, will be of the form exponential e power minus x by Lp into a constant. That constant will depend on the value here. The dotted line, however, will not be given by this, because you get this exponential distribution from the continuity equation when you remove this term. Dotted line is obtained when you include this term. Qualitatively you can appreciate why the dotted line has a higher slope at x is equal to 0 or near this depletion h. So this x is equal to 0 represents this depletion h here. Now why is this slope higher? What this slope indicates is that the current small I, instantaneous current small I, including the time variation or time varying effects, is more than the steady state current corresponding to the same voltage, okay, which is given by this slope. So this slope gives you the small I, whereas this slope gives you capital I, that is the current given by this equation, which is a steady state current voltage equation. You are familiar with this. Let us assume an ideal diode model for simplicity. Is is the reverse saturation current and Vt is the thermal voltage. Before explaining why is the small I more than capital I, that is why is the slope here more than this slope, let us plot the effects of this on a graph. So here we show the current I of t varying as a function of t, this dotted line, and another current capital I calculated by replacing the DC voltage V by the time varying voltage V of t. So this is your DC current voltage equation. Here I replace this V by this V of t. So that same equation is written here. So here I am going to replace this V by V of t. So result of this equation is a solid line, and this solid line is obtained using a distribution like this, whereas this dotted line is obtained using a distribution like this, which is non-quasistatic. Now the difference between these two is what is our interest. What is the difference? Why is this more than this? Now this can be appreciated from this equation. You see, when I want to get this distribution, I use this term and this term is set to 0. So if I integrate this continuity equation to find out what is the amount of current that is injected from this end, which is given by this slope, I will find it to be equal to integral of this as a function of distance, okay, which is nothing but the recombination current, that is the recombination in this area. But when the situation is time varying, I do not have only this term. That can be understood as follows: you replace, you shift this term to the left hand side, then what will happen is it will become delta by t plus, I remove it from here. So now when I integrate this equation with respect to x to get the current injected at this end, I have to integrate both delta p by tau as well as dou p by dou t. So I have to take into account an additional term, okay, that is dou p by dou t. Now because of this, the initial slope here is more. In other words, my current is going to be more under non-quasistatic conditions as compared to under quasistatic conditions. Okay. So now my goal is to find out how much is this slope because of dashed line or dotted line more than the slope because of quasistatic conditions. Now that I can easily appreciate as follows. Let me plot under quasistatic conditions the distribution of excess carriers for two different instants of time. So this distribution is for instant t, and for t plus delta t you have a higher excess carrier concentration because the value of voltage goes on increasing as your time increases. So this is for V of t and this is for V of t plus delta t. Now you see that between t and t plus delta t, the device has to store this much charge shown by the shaded region in the n region, so called neutral region. Therefore the current flowing into the device should not only supply for recombination in this region, but also it should supply the extra charge which is being stored between the instants t and t plus dt. That is why we can write an expression for the time varying current I of t as the current that you calculate assuming DC conditions plus dq by dt, where dq is the extra charge you have to store during the interval t and t plus dt inside the device. Now please note, the extra charge you have to store happens to be not only in the neutral region, that is this region here, but also at the edge of the space chart region. For example, when my voltage increases from V of t to V of t plus dt, your depletion region shrinks, okay. So this is a depletion region for t, this is a depletion region for t plus dt. So you have to store an extra charge because of shrinking of the depletion region. The depletion region shrinks on this side also, right. It is not shown here because when you draw the diagram to scale, the depletion region here is very small, that is why I am not able to show. Now the extra holes because of the shrinking of the depletion region, which happens to be the holes on this edge of the depletion region, are the same as the extra electrons which are coming in here, and therefore this shaded area plus this shaded area represents the excess holes being stored in the device from the instant t to t plus dt, and this is same as the shaded area. So this dq that we are writing here is sum total of this shaded area plus this shaded area or this shaded area. Now that is how you get your time varying current as the current obtained from the DC current voltage characteristics plus a term dq by dt. So that is the form of an equation wherein you find that the time varying current has been calculated using static or quasi static conditions. So this current voltage equation is under static conditions and this q is obtained from distributions under static conditions. So this is a so called quasi static approach in which the time varying conditions are modeled based on static or very slowly time varying conditions. Now here is an assignment for you. We wish to replace the distributed circuit on the left, that is this, by its lumped equivalent on the right, that is this one. So here you have an equivalent resistance R suffix E and equivalent capacitance C suffix E, and these are in parallel. The impedance Y looked into these two terminals should be the same as the impedance Y looked into the terminals of this distributed circuit. Now that is the goal. Express R suffix E and C suffix E, that is these two components, in terms of R and C. So R and C are the components of the distributed network in two ways. Quasi-static method, RE is given by delta DCI by delta DC voltage V, reciprocal, right, to the power minus 1, and C suffix E is given by delta Q by delta V, where V is a DC voltage. So what you are doing is you are applying a DC voltage V, finding out the current and charge through this circuit. So you are applying a DC voltage V, find out the current in this circuit and the charge stored on this capacitor for that voltage. Change the DC voltage to V plus delta V, find out the new current and the new charges, find out the difference in the two DC currents and the difference in the two DC charges. Those are what are delta I and delta Q here, and take the ratio of the difference in the DC currents and difference in the voltage and difference in the charges and difference in the voltage. That is the quasi-static method. The non-quasi-static method, it would be finding out R suffix in the following way as real part of Y of j omega, reciprocal, and C suffix C is imaginary part of Y of j omega divided by omega. What is Y of j omega? If you apply a sinusoid to this network and then find out what is the impedance that this network will present to the sinusoid, then you know that it is obtained as Y of j omega. You already know how to find out this impedance. Now that approach in our context of quasi-static and non-quasi-static method discussion is equivalent to non-quasi-static approach. Now compare the non-quasi-static expressions at omega tending to 0 with the quasi-static expression. Find out RE and CE in this approach and set omega tending to 0. See whether the results reduce to RE and CE. They may or may not. Please try it. Now classification based on frequency of voltage or current. After discussing the classification based on the rate of time variation of the voltage or current, the same information can be cast in a somewhat different form. Okay? So you can look at it as variation of the frequency of the voltage and current. Then the models can be referred to as either DC model when the frequency is 0 or AC model when the frequency is greater than 0, and depending on the magnitude of the frequency you can have low frequency, intermediate frequency or high frequency models. Let us show this with a diagram. So this is a frequency axis spanning a very large orders of magnitude of frequencies. So you can imagine this scale to be logarithmic. Now here this you have DC. On a logarithmic scale, actually if you want to show DC you cannot show, because f is equal to 0 will go to minus infinity. Okay. Low frequency is the region over here and high frequency is the region beyond a certain frequency, and in between you have the intermediate frequency. Now how do you quantify these ranges? Let us denote the transition between intermediate frequency and high frequency as f0. Then the transition between low frequency and intermediate frequency can be assumed to be 1/10 of f0. Now what is this f0? The f0 is equal to reciprocal of 2 pi into time constant, and that time constant depends on the context. It could be, for example, in devices equal to the minority carrier lifetime, or it could be transit time, or it could be dielectric relaxation time. So for different conditions the range of high frequencies and low frequencies are different. It depends on the situation and what is the appropriate time scale for that, and the time scales could be either minority carrier lifetime or dielectric relaxation time or transit time and so on. Now these time constants have been discussed in the module on characteristic time and length. Let us place the quasi-static and non-quasi-static models on this frequency scale and connect these descriptions to the frequency dependent descriptions. So S here stands for static, QS for quasi-static and NQS for non-quasi-static. So you see the boundary between the quasi-static and non-quasi-static occurs somewhere in the intermediate frequency range. In other words, your quasi-static models are valid for a frequency range beyond the low frequencies, okay? And on the other hand, beyond the certain frequency in the intermediate frequency range you have to use the non-quasi-static model even before you encounter high frequencies. The low frequency and quasi-static models are frequency independent but not necessarily identical. Now this part will be evident when we take the example of a diode. Here is an example of high frequency and low frequency models of a diode. The derivation of these equations it is assumed that you have done in the first level course. If not, please refer to the derivations in any book to understand the equations given here. Now diffusion resistance of a diode is given by Vt by Ia in a low frequency model, where low frequency here is a frequency omega into tau p less than 0.1. Tau p is a minority carrier lifetime in the n region. In the n region minority carriers are holes, that is why you have the suffix p here. However, for high frequencies in the range omega tau p greater than 10, in that region the equation happens to be something like this. Here we are not concerned with the derivation of the equations, but just to show you what difference does it make to the model equation or form of the model equation when the frequencies are low and when frequencies are high. So you find the high frequency region the resistance is frequency dependent, whereas in low frequency it is frequency independent. Same thing applies to the diffusion capacitance. Now note the difference between low frequency and quasi-static models. The quasi-static diffusion capacitance is equal to 2 times the low frequency diffusion capacitance, that is listed here, and so it is I into tau p by Vt. When you derive the p-n junction capacitance using a formula dq by dV, where dq is the difference in the charge stored in the device for DC voltage V and DC voltage V plus dV, that approach is referred to as quasi-static approach. On the other hand, if I use a continuity equation of this type, wherein I assume the holes to be varying sinusoidally with voltage and then solve this equation, then that is what is a non-quasi-static approach, and in that case you will get a frequency dependent capacitance. Now that is what is happening here, and in that frequency dependent expression when you tend omega to 0, then you will get this expression. So this is an example to illustrate the fact that quasi-static and low frequency values of a parameter need not be identical. However, both of them will be independent of frequency. Now R diffusion quasi-static on the other hand is identical to R diffusion low frequency. Now here is a plot of the ratio of the diffusion resistance to low frequency diffusion resistance and capacitance, that is the diffusion capacitance to low frequency diffusion capacitance. Now this is how it looks like. It has been plotted as a function of omega tau p. To consider the range omega tau p less than 0.1, you can see that the line here is almost flat. Omega tau p at 0.1 is this here. In other words, these parameters are not varying with frequency. This omega tau p greater than 10 refers to the region shown here. So it is in this range that these expressions will apply. In between range, however, the expressions will be somewhat more complex. If you want to know them, please refer to the books. Let us answer some questions after this discussion. Does inclusion of capacitive effect in an equivalent circuit amount to including non-quasi-static effect? Evidently the answer is no. We have just now seen in the previous slide that the capacitance can also be calculated from quasi-static conditions. So inclusion of capacitance does not mean that the model is quasi-static. However, if the capacitance is frequency dependent, then you can say the model is quasi-static, but mere presence of capacitance in an equivalent circuit does not mean that the model is quasi-static or it is including quasi-static effect. When can we be sure that an equivalent circuit model is non-quasi-static? From the discussion so far, it is clear that if you have a component in an equivalent circuit which is frequency dependent, then you can say that the model is non-quasi-static. Please understand one point. When we say capacitance is frequency dependent, this statement is not the same as saying impedance due to capacitance is frequency dependent. Impedance due to capacitance is always frequency dependent. For a capacitance C, the impedance is 1 by j omega c. So evidently omega is coming in the expression for the impedance, and the impedance of a capacitance will always be frequency dependent, independent of whether the capacitance has been derived under quasi-static conditions or non-quasi-static conditions. What we are saying is the capacitance itself will be frequency dependent if it is a non-quasi-static model. Does a non-quasi-static equivalent circuit model necessarily have a frequency dependent component? Well, the answer to this question is no, because consider a resistor, simple resistor. No matter what is your frequency, the resistance of this element will always be frequency independent and the value will be the same as that under low frequencies. Next, let us move on to classification based on the amplitude of the voltage variation. This classification is applicable to AC model. So you have small signal models and large signal models. Let us consider the example of a diode to illustrate the difference between them. Here is a small signal model of a diode. It consists of elements such as inductances, capacitances and resistances. Now the resistance and capacitance models could be either quasi-static or non-quasi-static. For instance, the quasi-static diffusion resistance model is dou DC current by dou DC voltage, where here the I stands for internal voltage, that is the voltage drop across the depletion layer, and reciprocal of this. The large signal model of the same diode would look something like this, where this C diffusion and C depletion are coming here in this large signal model also. However, these in this equivalent circuit the diffusion capacitance is quasi-static, whereas in small signal circuit it could be quasi-static or non-quasi-static. Further, the diffusion resistance is not there here, package capacitance or any series inductance in the large signal model. Often this model is used for lower frequencies. this diffusion resistance has been replaced by a current source dependent on the voltage. The Vi here refers to the voltage across the depletion layer. So in the context of the diode here, for example, the Vi means the voltage drop across this, whereas V is the voltage drop between these two terminals. Some voltage can drop across the neutral regions, and that is why you have the series resistance which accounts for this voltage drop in the neutral regions. V suffix I would be the voltage across this. So generally in the large signal model you will find not resistances but the current source dependent on the voltage. The equation for current as a function of voltage for large signal model is shown here. This is a SPICE model. We have introduced this equation in the second module, that is the introduction module earlier. Let us move on to classification based on starting point of the model derivation. So far our classification was based on the signals applied to the device, voltage or current signals. So we considered frequency, we considered time varying nature of the signal, and then we considered the amplitude of the signal. Now let us move on to the model derivation. There are two approaches that can be called as the rigorous approach, which gives a rigorous model, and a phenomenological approach that gives a phenomenological model. So what is the difference in the starting points of these two approaches? In the rigorous model, the derivation begins from the fundamentals or first principles. Example, from Newton's laws, Maxwell's equations, quantum transport equation, Boltzmann transport equation, etc. In a phenomenological model, however, derivation begins from the appearance of the phenomena rather than from the fundamentals, but the model is capable of predicting a range of observations and so is reasonably consistent with fundamentals. So you are interested in the equation for current as a function of voltage. As we have remarked, it is a very challenging exercise to start from fundamental laws like Boltzmann transport equation or quantum transport equation or Schrodinger's equation, and then get an equation for current as a function of voltage in a device where there are millions of carriers moving randomly and colliding with many particles. That is why you are looking at other approaches. So people say, why not you start from the appearance of the phenomenon and think of an equation that seems to match the experimental data over a wide range and it has some content of physics. Let us illustrate this idea using some examples. So one example of phenomenological approach is the drift diffusion current density equations. Equations for Jn and Jp listed here. Now these equations can be derived rigorously starting from the Boltzmann transport equation. For example, we have seen this in the module on equations of carrier transport. There we showed how Boltzmann transport equation can be reduced to a set of balance equations and how from the momentum balance equation, by doing a set of approximations, you can get the current density expression. So this is the rigorous approach. On the other hand, I can use a different approach, something that we have adopted in our first level course on solid state devices. There we said that I can assume the drift current of electrons as proportional to the carrier concentration n. Further, we can assume that all the carriers have the same velocity, drift velocity. Now this may not really be true, because you know that the picture is random and all carriers may not have the same velocity, but I am just making an approximation to derive a simple equation. Then I can multiply it by minus q, which is the charge, to get the expression for the drift current. Now further we can say that like the Ohm's law kind of behavior which we often observe between current and voltage, we can assume that the drift velocity is proportional to electric field. So if I assume this is proportional to electric field and put in a proportionality constant called the mobility of the electrons, I put a negative sign because the drift velocity is opposite to the direction of the electric field for electrons. And now I put all these terms together to get the formula Qn mu n into E for the drift current of electrons. I adopt a similar approach for the diffusion current. So I just like that say that the diffusion current of electrons will be proportional to the driving force, namely the concentration gradient, because we often observe the effects to be proportional to the excitations for small values of excitations. So we carry forward that experience of appearance of the phenomena here. Then I put an equality sign and put in a constant of proportionality and multiply by the charge to get the diffusion current. Next, I use a simple logic that when electric field and concentration gradient of carriers both present at the same time, in that case the diffusion current can be superposed over the drift current to get the total current. Now this superposition principle may not actually hold in practice, right? You may get some terms proportional to, let us say, the product of the concentration gradient and electric field. We do not know. If you do a rigorous derivation, some other terms can also arise, but then we use a simple logic of superposition of effects, and then we write Jn equal to the diffusion current Q dn grad n plus the drift current Qn mu n into E. Now this method of writing down the current density equation of electrons will be referred to as phenomenological approach, because we have made a number of assumptions and approximations based on our experience of a wide variety of phenomena to put together several terms in the form of a simple equation. So the same equation can be written in two ways: one, starting from the fundamental equations and then detailing a series of approximations to get the equation, or another in a phenomenological manner where we put down the various terms of the equation based on our observation of a wide variety of phenomena without bothering too much about how the equation that we write down is connected to the basic equation. Another example of a phenomenological approach is writing the mobility according to the Matthiesian rule. So when you say that reciprocal of mobility due to a number of scattering mechanisms is given by 1 by mobility due to one scattering mechanism plus 1 by mobility due to another scattering mechanism plus 1 by mobility due to another scattering mechanism and so on. So when you write this kind of an equation, you are writing it phenomenologically, because you are assuming that when several scattering processes are present together, the mobility because of these processes all present together would be the same as superposition of the results because of process considered individually, which may not actually hold, right? Another example of phenomenological approach is the assumption of a constant spreading current flow from the smaller contact of a spreading resistance to the larger contact. Okay, so this kind of a spreading assumption is phenomenological because you cannot connect it to any fundamental equation. Finally, an example of phenomenological modeling is the charge sharing model of threshold voltage of a short channel MOSFET. So this model we will discuss in the module on MOSFETs. You might have come across a short channel threshold voltage model based on charge sharing approach, where you assume that the charge in the channel of a MOSFET can be assumed to be partitioned into a part controlled by the source, another controlled by the drain and another controlled by the gate. this kind of partitioning is phenomenological because you cannot really show from some fundamental equation how you can get these three parts. Let us talk about classification based on the solution technique. The two types of models, it is a major classification, are analytical models and numerical models. This classification has to do with the approximation and solution steps of the device modeling procedure, which has 9 steps, square bar step. In analytical model, in the approximation step, you include the device specific simplifications of the equations and boundary conditions. EB stands for equations and boundary conditions, by neglecting some effects. So you neglect some effects and simplify the equations. So your approximations step will consist of the approximations done in the qualitative stage as well as additional approximations of the equations and boundary conditions. But in numerical model, you do not make any simplifications of the equations and boundary conditions. The only simplifications or approximations are those made during the qualitative step. And as far as the solution step is concerned, in analytical model, we use techniques such as calculus, algebra, geometry, trigonometry, etc. to yield the current or charge as an analytic function of the voltage. We will shortly see what is the meaning of analytic. Now in the numerical model, what you do is you transform the equations, E here stands for equations, using finite element, finite difference or Monte Carlo methods, so that purely arithmetic operations yield values of current or charge for specific values of voltage. In analytical model, you have an equation or an expression or a function for current as a function of voltage, whereas here you have a table of values in the numerical model, of table of values of currents for different voltages. Now let us look at the consequences of these differences. So because the analytical model includes device specific simplifications of equations and boundary conditions, the model is device specific and it is likely to be physically less accurate as compared to a numerical model which works for a wide range of devices and bias, because you are not making any simplifications of the equations and boundary conditions, and also the model is physically more accurate because all effects can be considered. Now because the numerical model transforms the equations using finite element, finite difference or Monte Carlo methods, the numerical inaccuracy is present in this model. However, the important thing is it can be controlled by increasing the amount of computation. Finally, an analytical model is computationally economical, whereas a numerical model is computationally intensive. That is the price you pay for including all the different effects and for having a model that works for a wide range of devices or bias. Important, the analytical model provides insight because you have a current voltage expression. On the other hand, because you are having a table of data points for current as a function of voltage in numerical model, the numerical model provides no insight. So that is the downside of a numerical model. Some interesting historical tips. The first analytical device model was proposed for the drain current versus drain to source voltage characteristics of the junction FET by Shockley in 1952. On the other hand, the first numerical device model was proposed for the collector current versus collector to emitter voltage characteristics of a one-dimensional BJT by Gummel in 1964. With that, we have come to the end of this lecture, and let us summarize the important points. In this lecture, we began a discussion of the various types of device models. Because the situation in a device is complex, it consists of millions of charge carriers moving about randomly and colliding with several particles and with each other, and because the conditions applied to the device can also vary widely. You can have DC, low frequency, high frequency conditions. The modeling of a device is a complex exercise. Therefore, many approaches exist. Some of these approaches we are considering in this module on types of device models. In the particular lecture, we first gave a variety of words which are used in the context of device modeling, and then we began a discussion of classification of device models. So, we considered classification based on the time varying nature of the voltage or current, based on the frequency of voltage or current, and then based on the amplitude of current or voltage. After that, we considered classification of device models based on the starting point of model derivation. So, we considered rigorous and phenomenological models. Thereafter, we considered classification of models based on the methodology adopted for solution. So, you had analytical and numerical models. We shall consider further types of device models in the next lecture.